Hi guys, hope that you're well. We're back with another video. This is one we've been waiting to make and highly anticipating making and releasing. This video would not be possible without the enormous support that we've had through this channel, through all sorts of different social media channels, and through your guys's and every other person's who's donated incredible generosity. This video to us, I think, means more than anyone we've done previously, because this is our huge, heartfelt and thank you, basically, to everyone who has supported us over the last 4 years. It's been an incredible journey, and today we get to basically show you what your donations have helped our charity create and do. So we were in London on the Tuesday
of this week, and we got the train up sort of lunchtime, and then we went along to King's College Hospital where all the money's going, and we just thought we'd be there for about half an hour really, just to meet a couple of people and then probably be on the train back home, but it was far from that. We were very privileged to meet some incredible people, and it was incredible to meet Dushi, who is the young woman who we have paid for a year, to actually see her working in Charlotte's lab, and it was incredible to see the lab as well. So as Miles said, this is a sort of accumulation of everything that's been done. I know that Charlotte would be so happy to know that she's not a statistic. She's, you know, she is somebody who is making a difference, and this will make a difference, I hope, to many families who, I hope they don't have to go through it, but if you have to go through it, this will make a difference. And I think with this video, we're solely going to do it on our visit to London. There won't be any stills at the end because we're a bit worried it might be quite a long video. And then the next video that we do, we'll give you all the other news that we've got, and I'll do a Q&A and some photos and things, but we just thought this is really important for this one.
The audio isn't fantastic. Nobody's fault. I think there's just quite a lot of background noise. So what I've done, I've basically added little subtitles to say what's basically being said and what's going on. But hopefully if you can turn your speakers up and maybe turn the bass down a bit, you'll probably be able to hear it all. So yeah, it's an incredible thing really, and I think it's the first time, you know, with the charity that we've thought, you know, wow, you guys and, you know, your generosity and, you know, the mission of the charity has actually made something, we've all made something together, which is actually making an active difference. As you'll see in this video, it's actually come together, and now there are tests going on, samples being made to try and help people with these terrible diagnoses and their families. So I guess we'll probably sign off there and leave it to you to...
I would just like to say that one of the reasons why we're thrilled with this is that some of Charlotte's results from various tests came back 3 months after she passed away, which is not acceptable, which is why we're backing what we're doing with King's and why it's so important to us that that never ever happens again.
Yes, I mean that's worth mentioning obviously, just for clarity's sake. What's basically going on in Charlotte's laboratory hopefully will speed up dramatically the time needed to get results and turn them around, get diagnosis as accurately as possible and as quickly as possible, because obviously when you're talking about glioblastoma particularly, you don't have a lot of time. As Mum just said, Charlotte's results came back 3 months after she died, and we want to turn that around to, you know, 5 days. And that's not just for glioblastoma, but other brain tumours as well, because frankly, it's just crazy the way it is. And hopefully with those quicker results, medical professionals will be able to act quicker, will be able to prescribe the right course of action in terms of medication and or surgery before the tumour has a chance to progress even further down the road. And of course not just getting them back quicker, but getting them back as accurately as possible, and hopefully the techniques that Dushi, our biomedical scientist, is working on will increase the accuracy and make sure this diagnosis are not only quicker but as accurate as possible, so the medication gets to the patient more quickly and it is targeted to the most accurate way possible to combat the exact tumour cells in their brain.
Yeah.
So we'll leave you there, and yeah, this video is for you guys.
Thank you.
Thank you.
Profiling in the diagnosis in gliomas, but it is the first line of diagnosis in brain tumours, and I explained why we want it to be like this, but it is the evolution of the markers for glioblastomas and brain tumours, which is an astonishing field in brain tumours and neuropathology. So just very simple facts about brain tumours. This is a slide from Professor Ashka, which I think it was done in 2014-15. So the data very similar, slightly different, but similar to this. So we have most of the cases of brain tumours. The most frequent one is the glioblastomas, which is about 35 per million. And 15 per million is about diffuse glioma, which is the lower grade gliomas, and there are a variety of conditions, and about 4 in a million pilocytic astrocytoma. This is sort of an estimate, but it is not a common tumor, but not rare, a tumor, a brain tumor, especially in children. However, the difference with brain tumors from other tumors is a very difficult tumor to treat. Very difficult to get into the brain, very difficult to resect. If it is persistent tumor, you have it in the breast, or you have it in the GIT, in colon, or in stomach, you can resect and you can function, the patients can function. But in the brain, every single cell counts. That is, if you remove the neurons, this cannot be replaced. And the dilemma, how much you can preserve, how much you can take out, how much you may take the tumor, but unfortunately you may die. So the treatment of brain tumors is of quite a lot of difficulty. Depends on diagnosis. Brain tumor depends on diagnosis on morphology. So the cells, how they look like, imitating the mother cells, and we call them astrocytoma because it is similar to astrocyte, oligodendroglioma because it is similar to the oligodendrocytes, and so on. And we see the similarity with other type of cells and try to make a diagnosis. But this is so much subjective rather than very objective. And the WHO and the classifications and the whole of neuropathology and histopathology try to make things very clear and narrow to make the diagnosis correct. So this is like tens of years of looking at different kind of tumors linking to the clinical diagnosis and make all sort of classification. But mainly the classification is how the tumor look like under the microscope. If you look at the glioblastoma multiforme, it's another big problem for diagnosis, because the glioblastoma is a heterogeneous type of tumor. If you look at the histology, there are now different type of histological appearances. We call them different type of names. But they are not similar kind of tumors. The tumors behave differently, affect the patients in different age group and in different regions of the brain. So the diagnosis of brain tumors, this is after 2016 WHO classifications, start to depend mainly on histology and genetics. So the genetics is very important to classify the tumors according to, we start with the IDH, and then the first step, and then the 1p19q, the ATRX, the TP53, and then the different kind of tumors. And the glioblastoma also have a different kind of tumors. If you look at, for instance, in glioblastoma, they are completely different from an astrocytoma or oligodendroglioma. They are all in the brain. We all call them gliomas, but genetically they are different type of tumors. They are not related at all. So the treatment now is different, and the prognosis is different. I'm glad to say that now most of the trials are linked to the genetic alterations. So this is what we do in the department. So we have 4 stages in the diagnosis of brain tumors. The first is the morphology, and again this is under the microscope. And then we do immunohistochemistry. Some of the antibodies are surrogate antibodies to the genetic alterations. And again we can assess this by microscopy. And then we have a single gene sequencing and multiple gene panels. Multiple gene panel is not ready yet, will be ready soon. But we have the single gene sequencing depending on what we think is important for a tumor to be investigated. So this is stage 3, and stage 4 is the DNA methylation. And this is how it is employed. I know it is a bit complex, but this is the flow of the diagnosis of brain tumors. First of morphology, and then we divide them to, and this is mainly about the gliomas, I should say. It will not apply to the others. To this category, and then we do immunohistochemistry, and then we try to divide them according to what they show, depending on their IDH status, the ATR status, ATRX status, and so on, to a different type of diagnosis. If we can get then to the genetic stage by single or gene panel, that will be added to the diagnosis and make the diagnosis firm. So all these color are where the genetic diagnoses are important to make the final diagnosis. And if we are in trouble and we don't know anything about a tumor, it doesn't go well with what we think we should be, we go for the DNA methylation. So for treatment and patients' survival time. So again, I'm going back to the way which we make the diagnosis now. The morphology about 24 hours, we get it. The immunohistochemistry to classify the tumor better take 48 to 72 hours. And then if we need the genes here, we select gene by single gene panel, take about 7 to 10 days. Sometimes it takes longer when we have the 1p19q because we do it in fish technique. And then if we are stuck with everything, we do the DNA methylation, and unfortunately it's taking a long time for us to do that. It is not the method, it is the selection of cases and the number of cases, because we cannot put one case at a time. It has to be a group of cases. So what we are proposing, and this is the base of the application for the grant, is that we scrap all this area where it needs longer time and single gene, and we stick with this intraoperative diagnosis. From there, we send it for DNA methylation.
I'm going to give a quick introduction, and then I'm going to tell you about what I'm actually doing in the lab, so the process in the lab. I'll make it a bit brief. So, brain tumours affect people of all ages, and they're the biggest killer of children and adults under 40. In the UK, every year, about 11,400 people are diagnosed with primary brain cancer, which is brain cancer that starts in the brain, and a further 16,000 people are diagnosed with secondary brain cancer, which starts elsewhere in the body and then moves to the brain. And there's about 120 different types of brain cancers, and the incidence of brain cancers is increasing rapidly, about 6% each year. So, as Safa said, originally tumours were classified by histology alone, so by looking at the appearance of cells under a microscope. So, as you can see on the pictures over there, there are two images side by side. But under a microscope, these images look very similar and can be diagnosed as the same tumour. However, when molecular tests were done on it, scientists found that they were actually completely different tumours that needed different treatment and had different prognosis. So lots of people found out that you needed molecular tests to define these tumours. So in 2016, the World Health Organization, they introduced molecular tests into their guidelines for classifying tumours, which was the first time they'd ever done this. However, there was still a significant number of tumours that lacked informative mutations, so they couldn't do any molecular tests for these tumours. And getting the, loads of people will tell you that getting the diagnosis of a tumour correct is really important for treatment. So methylation basically is when a methyl group is added to a cytosine molecule, and what this does is it changes the activity of the DNA without actually changing the sequence itself. And it's been known that changes in the patterns of methylation and the levels of methylation can have been shown to contribute to different types of cancers. So that's what they were looking at, and they identified that different classes of methylation corresponded to different tumours. And they've identified so far 82 different tumour methylation classes and 9 control tissue classes. And out of their research, they found that 25% of the cases that they put through this classifier actually had a changed diagnosis, and 50% of their cases had a refined diagnosis, so they were able to subtype it into a different subtype. And so they found that this had a significant impact on treatment and clinical management. So this is the same method that I've been using for the methylation assay. And so what we've done here is we've chosen 200 samples to test out this assay on. And it's a 5-day process from when the DNA is extracted to when you get the report for the tumour.
The only rules are, so if you're touching any of the doors with your hands, it's silver, red are for gloves. And then follow me.
Okay. I don't think we need goggles, right?
The main area where your magic happens will be in here. So everybody wants to maybe jump over this. So what we normally do in our processes, so a lot of the money ends up going on automation. At the moment, because of the small numbers involved in the validations, she's doing a lot of this work manually. It's quite intensive and it's quite hands-on. And so this is basically where you're spending most of your days. So the steps on the board, when she put on the Illumina, the pre-PCR steps, we're doing a hood up in the other end of the lab. So you have to separate it into pre and post PCR, because once you amplify up the DNA, it can cause contaminants in different areas. And then we do all the fragmentation and precipitation over here. So just to get you an idea of the kind of cost involved in our normal genomics, that piece of kit over there would cost about 150,000. That cost about 120. The scanner alone is about 120. I had to buy a new one of these last year. This housing that we just stack all our B chips in, so that we can do the lab stuff during the day, stack them in the scanner, go home, and just working through the scanning. The scanning on these would normally take, for one B chip, would normally take about anywhere between 30 minutes to an hour for kind of one of these. So we can do, what we normally do is every evening for genotyping, we would put about 6 plates on, so just under 600 samples every night. And that's for genotyping, that's not for the methylation. And then when we come in the next morning, so it's kind of 6 plates every day is what we do. But one of the reasons why, so we're working side by side, but we can't stop our automation at the moment to run, say, 16 samples. Because if we had to do it all automated for 8 to 16 samples, we'd probably have to charge £1,000–2,000 a sample. Because we've got, this is full every day, 600 samples, 600 samples, 600 samples. So the beauty is that, luckily having a dedicated clinical scientist here, she can run the samples because the small numbers with the validation. You can run them all, get all the steps done side by side. So obviously, because at the moment the small numbers, it wouldn't even be worthwhile doing on the automation. And then as soon as we get to the step where we're going to put them on a scan, because you can just add another few chips onto that loader,
Right.
and the next day we come in and it separates out the genotyping samples from because it's a different chip, it reads a totally different code, dumps the data off, and there's no sitting around waiting, or there's no bottlenecks, that we can just work. And that was when we were approached, we said, well, it doesn't have any impact on what we're doing, so of course let's do it.